This is lecture 1-7, which is the last lecture in unit 1 of solution reactions. This lecture is about titrations, and since you've done the lab now, you have a feeling for what a titration is. And so what I want to do is give you some background information. Please make sure, as usual, that you've completed your learning targets on your own first, and then come back and restart the video. So stop the video if you need to. Okay, here goes. So now that you've done this a little bit, the titration vocabulary, you should have a picture in your head of what's happening. And so what we have, usually a titration is either acid-base or redox, and it's a reaction in which we intentionally add just enough of one reactant to use up all of it and all of another, so that basically both reactants are limiting. And we use them to calculate the concentration of a reactant when you know the concentration of amount of another reactant. So there's some vocabulary that you need to know that's not included in your book, and that would be titrant and analyte. So the titrant is the thing that you're adding. It's the thing that's in the burette. Okay, and so when you're looking at your burette, the titrant is your concentration that you know, your solution that you know the concentration and the volume that you're adding, because you're going to add whatever you add from your burette. The analyte is the thing that you don't know. It's what you're analyzing. So the word analyte is the substance in the flask. It's the thing you don't know the concentration of, but because you put it in your flask yourself, you know its volume. So your analyte, or sometimes it's called the titrend. I don't like to do that because they definitely, titrant and titrend get really close to each other. So usually I use the word titrant for what's in the burette and analyte for what's in your Erlenmeyer flask. And you know how much is there, but you don't know its concentration. And as you know now, we use Erlenmeyer flasks because they're purposely designed so that you can swirl without splashing, so that you don't splash your stuff out. Okay, so a little bit more vocabulary, and this you did get from your learning targets. Equivalence point versus end point. The equivalence point is truly when you've added an equal number of moles of titrant to what you had in your analyte. Okay, so we call it the equivalence point because the moles of reacting titrant equal the moles of reacting analyte. And this is the purpose of a titration, is to add just enough so that you're using all the moles of each. All right, this is why it's called the equivalence point. We like this to be the same as the end point. The end point is when you actually stop titrating. So in your lab, we knew you reached the end point because the potassium permanganate stopped being used up. So what happens is that the purple stayed present up until then. The hydrogen peroxide was limiting, the hydrogen peroxide was excess, and the potassium permanganate was all used up. It was your limiting. But eventually you use all of your hydrogen peroxide, and now the potassium permanganate is excess. In a titration, we always have to add 1 drop extra. We ignore that. So I don't want you to be thinking about that. I don't want you to be focused on that. It's an error that occurs in every single titration. If you add more than 1 drop extra, this means you've gone too far and you've gone past your end point, right? We would like the equivalence point and the end point to be the same, but this depends on your lab technique. Remember, the same means the same plus 1 small little drop, right? So we'd like them to be the same, but it depends on your lab technique. If you went too far and your color change was too deep of a color change, then you actually titrated past the equivalence point, which means that your moles of reacting titrant appear to be more than they should be, which makes are more than they should be, which means that your moles of reacting analyte appear to be more than they are. So kind of keep that in mind. And remember that if this is an acid-base titration, we have to provide an indicator because most acids and bases are colorless. Okay, so let's talk calculations. The first thing you need, of course, is a balanced equation because you're going to need the coefficients. So this is first. It can be a net ionic equation or it can be a molecular equation. But if you're using the net ionic equation, you have to remember that you're solving for ions in your number of moles before you use your mole ratio, rather than solving for the compound. You basically need to start to make the practice of what you're solving for in moles has to be whatever is written in your equation. So kind of keep that in mind. Remember that in solutions, when we have ions in solution, maybe like in sodium carbonate, we have 1 mole of sodium carbonate, but that's actually 2 moles of Na plus ions and 1 mole of carbonate ions. And so you just have to get in the habit of whatever's written in your equation is what you're solving for as you're doing your stoichiometry. Okay, so the first thing you're going to do is write and balance your equation. Then you're going to begin your stoichiometry with the volume of the titrant, the one that you know the concentration of. So the one that you know both volume and concentration is where you're beginning, and you start with volume. All right, this is important because the volume allows you to use the concentration as a conversion factor to get to moles of your titrant. And then that's what this step is. Use the molarity of the titrant to convert to moles. Use your mole ratio from your balanced equation to convert to the moles of the analyte, because we're going to be trying to figure out something about the number of moles or the amount of the solute present in the analyte. And then you're going to decide what to do next based on what you're asked. So if you're asked for the molarity, you'll already have moles, and you can divide it by the original volume of the analyte. This is where you have to think about what you're doing. When you're doing limiting reactant and what's the new concentration after you pour two things together, then you're using new volume to find new concentration. But if you're asked to tell me what was in your flask before you reacted it, now you're going to use the original volume to tell me the original molarity. Okay, so this gets confusing and you have to really think about that. So if you need to, pause this and replay that little spot so that you can hear it one more time. If you're asked for percent by mass, then you have to convert your moles of your analyte to grams. And then again, you're looking for in an original solution. So you're going to do grams of your analyte divided by grams of your original solution. And this is what you're doing in your hydrogen peroxide lab. Okay, so we'll do some of these calculations in class and you'll see what I mean, but remember, keep it straight. If it's a titration, you're solving for the original concentration before it reacted, so you are dividing by the original volume. If it's a limiting reaction, a reactant calculation, like in section 1.6 and learning targets 1.6, then you're usually looking for the concentration after the reaction, so you have to use the volume after they're poured together. Okay, replay that again if you need to. All right, we're going to do a couple of examples so that you can see how this works. And so take a second, pause the video if you need to write this question into your learning targets, and then go ahead and restart it. Okay, so in this case, we have 26.25 milliliters of 0.185 molar sodium hydroxide. That tells me that I know the volume and the molarity. This is what's in my burette. This is the titrant, okay? And I'm reacting it with 25 milliliters of sulfuric acid, and I want to know the molarity of the acid. So this is the analyte, okay? And so if I'm solving for molarity of the acid, that means that I need, moles of H2SO4 to divide by liters of H2SO4, all by itself, original solution. So I already know that the volume is 0.02500 liters. That was given to me here, okay? So now I need to do stoichiometry to figure out the moles of the H2SO4 to put into the numerator. Just kind of picture that this is what you're doing. Okay, so I'm going to start with the volume of the one that I know the volume and the molarity of, the titrant. And that would be 26.25 milliliters, or I'm going to go ahead and put it in liters, 0.02625 liters. I did not write my equation yet, so I'll need to do that. And actually, let me make some space up here so I can do that easily. I'm going to go ahead and write this as a net ionic equation so that you can see how this works, just once, how this works. If we were doing it in a molecular equation, it's actually easier in this case, but I'm going to write it as a net ionic. So sodium hydroxide is a strong base, and sulfuric acid is a strong acid. So OH minus plus H plus yields H2O, and this is my net ionic equation. Okay, so I'm going to start with my liters of solution. Remember that this is my sodium hydroxide solution. I'm going to convert liters to moles, and this is going to be to moles of the whole sodium hydroxide compound. All right, this is using the molarity that they gave me, so 0.1850 moles in 1 liter. Now, before I can use my net ionic equation, I don't have NaOH. It's represented by the OH minus in my net ionic equation. So I have to say moles of NaOH to moles of OH minus. I would not have needed to do this step if I was using the molecular equation. So I'll compare that for you in just a second. In NaOH, there's 1 OH minus, so I can do that. Now I need to go to my acid, and in my equation, my acid is represented by the H plus. Okay, so I'm going to come back in and convert from moles of OH minus to moles of H plus. And from my net ionic equation, I have 1 mole of each. Okay, I have to get this stuff out of my way, sorry. After I've done that, I didn't ask you about H plus, I asked you about H2SO4. So I need to go from moles of H plus to moles of H2SO4. And remember, we're trying to solve for moles of H2SO4 so we can find the molarity. Again, if I was not using a net ionic equation, I wouldn't need this step, but my equation would be balanced differently. All right, so in 1 mole of H2SO4, there are 2 moles of H plus shown here. Okay, so now I can solve for moles of H2SO4. And when I do this, I get 0.00248, say 0.0024281, etc. And this 8 is my last significant figure. Okay, and this is moles of H2SO4. So if I want molarity of H2SO4, I'm going to do moles of H2SO4, 0.0024281. I'm just going to carry it in my calculator, but remember that I have 4 significant figures, moles, divided by my original 25 liters of solution, not a combined volume, just my original 25 milliliters of solution. So this will be 0.02500 liters of solution originally. All right, that's going to give me a molarity of 0.097125, which comes out to, with significant figures, I actually have 4, so 0.09713 molar H2SO4. Okay, so I want to show you what this would look like if it were the molecular equation. And so when we do the next one, I'll do it with a molecular equation instead, and that will help you see how this works, right? You can decide which way you like better. Okay, stop the video to write the question. Then you try to write your molecular equation this time, not a net ionic, but a molecular, and then restart the video. Okay, so I have barium hydroxide and hydrochloric acid. And when they react, that's going to give me water and barium chloride, which is BaCl2. If I were writing the net ionic equation, it would be OH minus plus H plus yields water, because these are strong base, strong acid. Very similar to what's up here, except that this time it's my base that has 2 hydroxides instead of my acid having 2 hydrogens. Okay, I need to balance this equation. So I need 2 Cl's, which is going to give me 2 H's, and I have 2 OH's and 2 H's, and that gives me 2 waters. So notice that now up here, my coefficients were 1s, but in here I'm balancing this for the OH minuses with my coefficients here. So again, we're going to identify the titrant and where we're starting. I'm neutralizing 50 milliliters of a 0.1 molar solution. This is actually, now we're actually solving this a little bit differently, finding the volume, which is kind of weird, okay? So we actually have to start with the one that we know both volume and molarity of, which is my hydrochloric acid. So I'm gonna go it's not really a titrant, this is actually probably what's in the flask, and we're looking for the volume of titrant, kind of weird. We would never do this for real. We could do it if I were trying to figure out how much I was expecting you to use, so I would know how much solution to make in the lab. Okay, so I'm going to do the volume of the titrant is what I'm looking for, which means I'm starting with the one that I know volume and molarity. And I have 50 milliliters, or 0.05000 liters of solution And from liters of solution to moles of who's in there, which is in this case HCl. And this is my molarity, so 0.1000 mole per liter. Now HCl is actually in my equation, and HCl is here, so I don't have to go to the ion. Instead, I want to know about the barium hydroxide solution, so I'm going to go ahead and go to the barium hydroxide. Okay, so this is going to be moles of HCl to moles of barium hydroxide. Notice up here I had to go to the ions because the ions were in my equation. Here they're not. I can go straight to the compounds. So this is 2 moles of HCl for 1 mole of barium hydroxide from the coefficients in the equation. And I want the volume of that. So since I have moles, I can use the molarity to get to volume. And that means moles of barium hydroxide are on the bottom, and volume, or liters really, I should put liters there, volume of solution in liters on the top. This would be from the molarity, 0.1292 moles for every 1 liter. And I can do the math really quickly. I get 0.019349 and more numbers, but I have, let's see how many sig figs. 4 sig figs, which would be 0.01935 liters, or if they wanted milliliters, you can convert it back, 19.35 milliliters of my barium hydroxide solution. Okay? All right, I want to do one more where you have to find mass percent, because this is actually how a lab would find blood alcohol percent. So take a second to copy the question and then restart the video. Okay, so they gave us the equation, and it's a balanced equation. This is a redox equation. It doesn't change how you do it, all right? You are titrating plasma, blood plasma, so this is a mixture, and it's your analyte. It's like a solution, it's just blood plasma is a solution. And we want the mass percent of alcohol in blood. So picture working backwards, that mass percent of alcohol will equal grams of alcohol over grams of plasma or grams of blood, right? Times 100 to make it a percent. So I'm out of space, times 100 to make it a percent. So in order to solve this, what do I know already? I know my grams of plasma. They're going to go in the denominator. I have to do stoichiometry to find grams of alcohol. Okay, so I'm going to come down here because it's cleaner. I'm going to start with my titrant, which is the one that I know both the volume and the molarity, and I'm starting with the volume. And so you can actually try this yourself if you want. Stop the video and see what you can do. All right, so this would be 0.546 liters of solution. And this is my dichromate solution. And so I'm going to go from liters of solution to moles of dichromate, and they actually react this like this in the lab. The molarity is 0.05961 mole per liter. And now I need to know alcohol. So I look at my equation and I see the alcohol here and the dichromate here. So I'm going to put moles of the dichromate ion, which is actually in my equation, there, and moles of the alcohol, C2H5OH, ethyl alcohol, there. From my equation, this is 1 mole of alcohol for 2 moles of dichromate. And remember that I need mass of alcohol, so I'm going to go on from moles of C2H5OH to grams of C2H5OH. And I used 46.08. I probably should have used 0.016 for hydrogen, but I used 1.01. Okay. When I do that, I can do my math and figure out here per 1 mole. I can figure out that this is 0.04871 grams of C2H5OH. My significant figures are 4 from everything that I've got. And so technically I can stop here. That's a 0. And I'm going to come back and say the percent of alcohol in the blood would be my 0.04870 grams of C2H5OH over my 28.00 grams blood plasma times 100, which gives me then, remember this is in the original blood, right? Gives me then 0.170714. I have 4 sig figs, which is 0.1707%, which is, oh no. Let's go back and look. Is this person drunk or not? This is what they do. They tell me that we're analyzing this to decide if they're drunk. You should know that in the state of Virginia, 0.08 means that you are drunk, 0.08% blood alcohol. This is 0.17% blood alcohol. This person is drunk. They are almost twice as much alcohol in their blood as they should be. So this gives you an idea of how to do calculations related to titrations, a little bit of the vocabulary related to titrations. Be ready to come and practice and ask questions in class.